Okay. Good. All right. Now, we ended yesterday talking about chemical changes and all the evidence for a chemical change, how you know a chemical change is going on. I'm going to start classifying chemical changes now according to a couple of different things. All right, and that's what I want to show you today. But I'm going to start it off with a little demonstration. Okay, I'm going to take this chemical. It really isn't important what it's called, but it is ammonium thiocyanate, and you don't know what that means. And I'm going to take this chemical, and this is called barium. Oh, I didn't get all that out of there. Get all that out of there. Barium hydroxide. That's this guy right here. Put him in there. It's not important what they are, but it's important we notice what's going on here when I add these two guys together, okay? So I'm going to mix them up. Now, it's just too solid. Can you all see that? I have to keep this a little bit lower today because of videotaping it. I'm going to mix these two guys together. They're two, dry powders, but yet as I mix them, you'll notice something happening, hopefully. Anybody see what's happening? Kind of in the front here. What do you guys see? Yeah, it's turned into like a slush. But now it's a liquid. It's kind of weird. That's strange. It's supposed to happen? Actually, it's okay. Fear not. Alright. Now, mix those two guys up. I stirred them up. And we can see, probably got a chemical change going on here. All right, but I want to talk about what kind and how we know. And that's why I need somebody strong. All right, we'll take this Kyle's a little closer, whatever your name is. Come up here. Come on around this way, because just watch yourself. All right, I'm willing to bet that Kyle can't pick this up. I've done something to this that he can't possibly pick this up off of. Wait, now don't go shoot. This is chemical, bad chemicals. Nice and gently. Grab this speaker and pull it straight up. See if you can remove. I don't think you can. I don't think you're strong enough. Go ahead. Ah! Get that hand off of there. What? Pull it, keep going. What? Okay. All right, good. Well, now, Kyle knows what happened. Did I super glue this on here? Hold it down low there. What happened? It's cold. It's cold. What do you think it did? Probably froze. It froze. It froze on there. That's one way. You could have a seat. Thank you. That's what I need a Kyle for. Told you couldn't do it. I win. You owe me $100. I told you you couldn't do it because it froze on. I put a little water on there and it froze when I mixed the two together. That's one way, one type of reaction I want to talk about today, the kind that get cold. We're going to call that a certain name. By the way, I'm going to come back to this in a second because, actually, I may be able to do it right now. The other kind, well, I can actually do two at once here. The other kind are ones that, well, if this one got cold, what do you think the other one's going to do? Yeah, it's going to get hot. And that's this right here. Neat little thing. You ever see these? Who knows what these are? Come on, no survivalists here, no army, no military. Well, actually, that's true. They kind of look like that, and they do use the same basic principle, but not this particular one. You ever hear of MREs? You know what an MRE is? They talk about that in the military. They have meals ready to eat. They're basically packaged meals, and these will come with it. All you have to do is add a very tiny amount of water. You open it up, rip it open, and you add a little bit of water to this, which I will do. And I don't need much, just a little bit in the bottom. And you lay it flat. And you put this inside of your meal, ready to eat. Put that right inside of there. And what will happen is, I get enough water in there, move it around. There's a chemical reaction that goes on inside of that. All right? And it takes a little bit of time, so I'll let it go for a second. While I'm doing that, I want to show you, the stuff I added to this. There's a couple reasons why I do demos, I told you. And here's one of the reasons. I want to show you some of the hazards of these guys, too. Turns out that this particular, one of the chemicals I use here, barium hydroxide, is nasty stuff, very poisonous. All right? But you wouldn't know that just seeing it in a jar like this. So you got to treat it with caution, with care, and respect. Now, I could just dump that down the sink, but that would be bad, right? I don't want to kill a fish. But I can actually make it non-toxic, basically. by adding something else to it, another chemical to it, sodium sulfate. And watch what happens. This is kind of a clear solution. And if you can see here, when I add the sodium sulfate, I will get, when I stir it up especially, I think, you will get it turn to like a white precipitate. And that's good, because now I have made this less toxic. Okay? Actually, some of you have drank this before. See, barium hydroxide was in that. You can't drink barium hydroxide, you'd be dead. But you can drink barium sulfate. Some of you have. Oh, but look what happened here. See what's happening here? Yeah, you see it? Getting bigger? It's because why? What's it doing? Yeah, it's heating up, forming some steam in there. It's getting hot, very hot. That's what they cook their food with, the MREs. They cook their food with that. Look, see the steam coming out here? See that? You'll see more of it in a minute. But back to this guy right here. Or watching that guy. Well, it kind of smells though, too. See the steam coming out there, right? So we have two kinds of reactions. Those that get cold, those that get hot. I'm doing two things at once here. Where have you drank? Anybody ever had what's called an upper GI or a barium swallow? You have. And you have. I have. I've had actually a couple times. It look familiar? It's like a really thick white milkshake you drink. And while you drink it, this is getting a little hot now. While you drink it, they're taking a picture of you with an X-ray, right, as you're drinking it. And they can actually, because this barium is radio opaque, which means it doesn't, the X-rays can't pass through it. You get a nice picture of your esophagus and all the way down into your stomach, and even a little further probably than that. Not much further, because then you have to, you have to do a lower thing, and then you have to have a barium enema, which you don't really want that. We don't want to talk about it. Anyway, but yeah, this stuff I can drink. And the reason I can is it's not soluble in water. It won't be absorbed by you. If I absorb that barium ion, it's very poisonous. Now it's barium sulfate, it just goes right through you. Okay, it just goes right through you. It's not digestible. All right, I'm going to dump that down the sink now that I've made it less toxic. Okay. And we're finishing up our other one over here. You can see it's all steamy. What was that doctor in Dr. McDreamy? Or McSteamy? I don't know. You might have been steamy. I don't know. That was in House, right? House? Was it in House? Right? Was it House? You guys ever watch House? You're too old, aren't you? I mean, you're too young. House was a big deal back in the day, but not anymore. All right, so there you go. I don't want to notice casting aspersions on House. Maybe he's watching right now. Sorry, Mr. House. He's British, you know. He's actually British. Has anyone ever seen the show? No. All right, I'm going to get this guy out of the way, even though he's very, very hot. So that's how you would cook your meal. That's how you would cook your meal. If you were in, the jungle or in the desert or someplace where you could cook it anyway. You took that light off for me. You would cook it like that. All right. So we got two kinds of reactions, and we're going to classify them. And I think I hinted ahead yesterday at the end of the period. Maybe you remember. What are the two names I'm going to give for the ones that get hot and ones that get cold, ones that release or absorb energy? And remember, they both begin with E. Maybe I don't think I gave it to you. I actually didn't think about it. Energy is what's being released or absorbed. What's the name of, what do we call it? How are we going to classify these? What are the two words? You've heard them. I know you have. Definitely heard them. Probably in biology. Definitely in middle school sometime. It was an E. If I go out that door, what do I call that? What could be a sign above that door? Exit. Okay, kind of sounds like that. Exothermic, or exogonic, whichever you want, one of those two words. Or, what's the other one? Endothermic. Right, those are the two kinds. We have exo and endothermic, or exo or and endogonic. All right, we're going to use, I hate saying that word, I'm sorry. I know it's more precise, but I'm going to say exothermic and endothermic. It's just easier for me to say it, and I've been saying it like that forever anyway. Those are the two kinds. We're going to talk about each of those right now. All right, two types of chemical reactions. We're going to classify. Notice how my notes go. I hope you're realizing this, how my notes go. This is number 2 underneath what? Chemical, no. Look again. Look at your notes. Evidence of a chemical change was number 1, wasn't it, right? And that one had A, B, C, D, correct? So this can't be number 2 under evidence of a chemical change. This is number 2 under what? Chemical changes or chemical reactions. So the first thing about chemical changes I talked about was how you know one is going on, what's your evidence of a chemical change. That was 1. Now, this is number 2. How do we classify chemical changes? We classify them a lot of ways, a lot of different ways, but we're going to classify them today by virtue of whether they give off or absorb energy, whether they get hot or cold. Okay? And we're going to talk about all of the different possibilities. Now, you've seen those words before. Somebody did come up with them, and I waited enough and gave you enough hints, you got it. But you probably only, in the past, memorized. I'm going to give you a little bit more information on that. And you know what? A little bit more information, a lot more information in AP Chem 2. We're going to be doing actual calculations with it. Actually, even by the end of the year, we'll be doing some calculations with energy. Not many. Way more in AP Chem. All right, so let's talk about, you don't have to skip that much line, just right underneath. I had to do it because of the way my PowerPoint's set up. Endothermic will be right up. We'll talk about him first. Do you know which one was the endothermic one? Well, let's think about what's happening in an endothermic reaction. Here for the voting papers. Oh, they had a vote at the beginning? They didn't get it yet. Can you come back? I haven't given it to you yet. All right, end of the period? Yeah, thanks. Okay, I knew I had to give them to you. I was just going to wait till the end of the period. All right, endothermic. Which of those two do you think was the endothermic reaction? Well, let's think about what happens. The word exit, exothermic, you think of things going out, right? Exit, exiting. That means releasing something. Endothermic is the opposite of that. It's going to be absorbing something. Okay? So that's what that means. All right, and I'm going to graph this. I want you to draw this graph. You don't have to have arrows at the end. But I want you to draw this graph. All right? And I want you to realize something in an endothermic reaction. In an endothermic reaction, and this is energy versus time. You also want to put time on the bottom of that one. See, you would have just had a definition, which one's absorbing, which one's releasing, and that would have been the end of it, I think. Well, in chemistry, it's different. I'm going to show you an endo or exothermic reaction like I just did. We're going to see others throughout the year, many. We're going to eventually do calculations with the people. I'm going to graph what's going on in this. I'm going to talk about whether it feels hot or cold, what's going on with the reactants and the products and all this stuff. All right? So this is the first real day of chemistry. Up till now, we've been kind of doing, some basic preliminary stuff. We're going to get some real chemistry today. Okay? If something's endothermic and it's absorbing energy, it must be, here's the reactants. Those are the guys on the, before they react. Here are the products. That's what's made from the reaction. The products have to have more energy than the reactants. That just makes sense. Okay? I don't really want that to show up right away. The question then becomes, how does this get there? I kind of gave away the hint there. You can start the reactants, black. And, you could think, well, if you just go straight to the products, okay, like that, don't do that. All right, but it doesn't really do that. It actually has this weird shape to it I want to show you, okay? And if you look at it, you don't need this line or this line on the bottom. It's just the only graph I could find online here. And it actually has this little hump in the middle. So draw that little, weird-shaped graph, and I'll try to explain what's going on there. You don't need numbers here either. I didn't tell you that, but you really don't need the numbers. It's not important. It's just a matter of energy is on the y-axis and time is on the x-axis. So as this reaction proceeds, you go from reactants that have, remember we were doing some reactions yesterday, right? Yesterday, I wrote down at one point, HCl plus NaHCl3. And then I got salt, carbon dioxide, and water. These are the reactants. Those were the products, okay? In order for these guys to get over there, remember we talked about this yesterday, they have to break these up and rearrange it. So this chlorine gets together with that sodium. You get sodium and chlorine together, sodium chloride. You get one of these H's and one of these H's get together, one of those O's, you got water. Well, in order for that to happen, the first thing it has to do is you got to break up those reactants over here, okay? That takes energy. That's why this graph goes up at the beginning. When these new products on the other side form, you actually get back some energy. You actually get back. So that's why it goes down at the end. We'll talk a little bit about that. I'm going to do a little bit more at the end of this one in a second. But now let's write some actual notes down for each of these. Ready? Endothermic. Absorbs energy. It started at a low, ends at a high energy. I'm going to tell you right now, people, you're going to get one of these graphs, either the endo or exothermic, on the test, at the end of this chapter, sometime next week. Okay? You can memorize your way through all the notes I'm going to write on here. You can. But you can also just look at the graph and answer most of the questions. I could tell this guy's absorbing energy because he started at a low energy, reactants are on the left side, and it ends up at a product at a higher energy. So he must have absorbed energy. Okay? Now, if he absorbed energy, my question then becomes, how would he feel compared to a guy who gives off energy? Think of it that way. I mean, sometimes it's easier to think of the other guy. A guy who releases energy. What are some things that give off energy? Fires, right? They give off energy. So if this guy's absorbing energy, how's he going to feel? Which of those two that I did you think was the endothermic reaction? The hot one or the cold one? The cold one, yeah, the cold one. These are going to usually feel cold. And by the way, that's all relative. It's relative to where this is happening. They're always absorbing energy. They're not always going to feel cold. That's why I put the word usually in front. All right? Because if something happens, something's absorbing energy at a temperature above your body temperature, you're not going to notice that it felt cold. Okay? And the opposite is true, too. All right? For example, how do you boil water? Is boiling water endo or exothermic? See, that's what everybody says, exo, because water feels hot. Boiling water feels hot. No, not at all. To boil water, does the water have to absorb energy or is it giving off energy? It has to absorb it. You got to put it on a stove and give it energy, don't you? So boiling water is an example of why I told you chemistry's harder and easier, I think, than biology. Biology, if you're good at memorization, you're okay. You can memorize a lot of stuff and you can spit it back. You're pretty good at that. Same thing with history, same thing with a lot of other classes. Chemistry, you got to understand it. You got to apply it. It's not enough to just memorize, absorbs energy, usually feels cold. Okay, you got to be able to apply it. And that's what I'm going to have you practice with some examples pretty soon. Okay, so it feels cold usually because if it's, again, not all the time. What else can I say about it? Well, things like this, it turns out, I want you to look at the shape of this. The reason we're graphing, sometimes you see things in a graph you don't see otherwise. If this were a hill, and we look at it like a hill, I'd be surprised. I'd be very surprised to see a ball at the bottom of this hill, all by itself, get to the top of the hill. I'd be very surprised by that. Right? It doesn't usually happen by itself. These guys, I'm kind of getting ahead of myself. All right, well, you can see right now the products contain more energy than reactants. You can write that down. I'm getting ahead of myself. I wanted to say something else here. They contain more energy because they were absorbing energy the whole way up. I'm going to draw a reaction underneath this in a little bit and show you exactly what's happening. I want you to draw it too. Just a generic reaction. All right. In order for it to absorb energy from somewhere, when I'm picking that up, when Kyle was picking that up, he was absorbing energy from his hand. That's why it felt cold. That's why it felt cold to him. Okay? Well, that's not usually going to be a spontaneous reaction. It's not going to happen all on its own. Balls don't roll uphill by themselves without any help. You got to push the ball up the hill, right? You got to give it a push. And that push is the energy you're putting into the reaction. It's getting that energy, in the case of this guy, from me stirring it and from the heat in the environment around it. It's taking that energy and it's turning it into new products. Okay? So in a reaction like this, here's what you could say in the end. This is a final summary of what's going on here. All right? You got to do this. And I want you to actually draw this little reaction here, and then I'm going to have it show up here. I want to make a general formula. I drew, 3 or 4 reactions on here yesterday when we were doing our demos. Let's just use a generic formula of AX plus BY yields. One of my reactions was an exchange like this. Write that. AX plus BY yields. Now, what can I do to exchange places on these guys? What could I get here, do you think? Something like AY plus BX. Okay, so there's a chemical reaction. These guys are the reactants. these guys are the products. Okay? What I'm saying in an endothermic reaction is this. You got to put energy in. You got to put energy into this to get it going. Oops. So, first thing you got to do, don't draw this on. Just listen to me first so you understand it. This is why, by the way, it's really nice to have the video. Not just, if you were to copy these notes, you're not going to get the demo, and you're not going to get my explanation here, which is kind of the key right now. In order for this, A and X are bound together. They're stuck there, whatever that AX is. In order to get those guys to come together with Y, A and Y get together, I got to break these bonds, and I got to break these bonds. Don't do anything. Just watch. Okay? When those bonds are broken, it takes energy. Maybe let's just say, I'm just going to make up a number. Let's say it takes 100 units of energy. You don't even know what the units of energy are. Now, when these guys over here come together, when A gets together with Y and B gets together with X, guess what happens? Energy is given off. In the case of an endothermic reaction, the energy you put into it is greater than the energy you get back. But it does explain this little hump. When I get the new things forming, it gives back that energy a little bit more. It drops down a little bit. So maybe I get like 20 units of energy when these new guys are formed. You see? And that is why the graph looks like this. This is your input of energy here. That's your 100. And here's your 20 coming back. Okay? It gives that much off when the new products are formed. Okay, now you can try to write that all out there, but it won't make a whole lot of sense to you unless you were here to see it. See what I'm saying? You kind of have to be here to understand what's going on in that case. Maybe it still doesn't make a lot of sense. But even if it doesn't, I'm going to erase this and show you. The last thing, in words, this is what's happening. Before you write, listen. More energy is required to break the bonds of the reactants, all right, than is released when the new products are formed. Okay? Write that down as your final summary of this. I'll give you a second to write that. Now, that was an endothermic reaction. The next one will not take me as long, okay, because now you have an idea. I've explained this one pretty well, hopefully. Maybe you didn't quite get it. On the next one, hopefully you will, all right, and I'll try to explain that one. But basically, that's an endothermic reaction. That was the cold one. That was the one with a little peak. Now, what about an exothermic reaction? That would be next. And the way you remember this at the end, you know, the words exo, exit, expel, give off, right? That's what it means, right? You're going to draw the same basic graph, but this time, look at the shape. Look at the shape of that graph, okay? Same basic idea. Reactants are on the left. Products are on the right. This is energy. This is time. And over time, what's happening? But compare that to the one we just saw. Look at how they're different. See if you can figure out why they're different like that as we go along with this. So you want to draw the same basic shape to this graph here. Now, again, the other one was just a second ago, but I'll show it to you again. The other one, don't have to draw this. Look like this. See the difference? Okay? This guy, you put in a lot of energy. This is the last one from before. And you only got a little bit of energy back. Here, you put a little bit of energy in, and you get a lot of energy back out. All right, it's kind of like, if you think of it as investments, you can kind of think of it that way. Here, I buy, a Michael Jordan card for 25 cents when nobody's an unknown, and then I can sell it for $1,000. I get back a lot more than I put in. So in the other case, I could also make a bad investment. I could buy who was a flop in the NFL. Supposed to be really good, but he stunk.
Tim Tebow.
Well, actually, I think Tim Tebow's cards are still probably worth a lot, though. Because he was very popular, at least. I'm talking about guys who were supposed to be good, like quarterbacks that were supposed to be big. But you're right, Tim Tebow would probably be a good example. You put in, you buy it for, he's going to be worth a lot of money, and then you only get a little bit back. All right, that's like an endothermic. You put in a lot of stuff. Let's make a prediction. Who's being the big names coming out of the draft this year? Who? Manziel. Good. That's a good one. Who said that? Yeah, that's a good one. What will Manziel be? You want to take a chance and spend a lot of money on his card? Or is he going to be a flop and out of the NFL in a year? Right. Is he going to be exothermic or is he going to be endothermic? That's the question. All right, well, either way. This is exothermic, and here are the kind of questions I'm going to ask you about this graph. I might ask you, is this going to absorb or release energy? Look at the graph. Can you tell what it's going to do? Is it absorbing or releasing energy, this guy? He starts out up here. He ends down here. What must have happened? He must have given off that energy. Okay? Oops. He released energy. If he's releasing energy, what's he going to feel like? Think. Hot. He's going to feel hot. Usually going to feel... Now, again, it depends on your temperature, your body temperature, whether you're going to feel hot or it's going to feel hot or not. For example, I used it as an example a minute ago, boiling water. Boiling water feels hot, but it's an endothermic process. I got to add heat to the water to make it boil. This is weird. You're not going to believe this. But freezing an ice cube is an example of an exothermic process. If I take liquid water and freeze it, in order to do that, it has to give off energy. I got to put it in the freezer and it sucks energy away from it. All right, that's an exothermic process. It actually gives off heat. What? Ice gives off heat? As it's freezing, ice actually does give off energy. It's weird. But because it's happening at a temperature below your body temperature. Now, we will, in the course of this year, see something freeze at around or above your body temperature, and you'll feel the heat given off when it freezes. All right, you actually feel it, and so is ice doing that. You just can't feel it because it's below your body temperature. The reactants, as you can see, contain more energy than the products. In the case of an exothermic reaction, they start out high and they end up low. And these guys are more likely to be, they're going to favor being spontaneous. I'm going to put down, this is actually a lie. Anyone who's watching this is watching me and thinking to myself, who's had a real chemistry and done some real thermodynamics, and said they're not usually, it just favors spontaneity. It's more likely to be spontaneous. It wants to be spontaneous. This is more likely to be. But there's other factors involved, two other big factors involved on whether a reaction really is spontaneous, and we haven't talked about those yet. But it would not be as surprising to see a ball roll downhill, assuming that little hill's not in the way, a ball roll downhill, okay, than it would be to see a ball roll all the way uphill, okay? So it is more likely to be spontaneous. And finally, my little summary here, again, less energy here is required to break the bonds of these guys than you get back. You get way more back, and I will draw my same reaction, generic reaction here in a second, after you copy that. So, again, real quickly, if I have two guys, AX plus BY breaking up into AY plus BX. I'm just using generic letters. Obviously, these could be salt, they could be sugar, they could be water, they could be the only chemicals you know already. But I'm going to use these because it makes it a little bit easier. Here's what I'm saying. To break this guy, to break that guy, might take, 30 units of energy. But when I get back this guy and this guy, when they form, they may give off 150 units of energy, and therefore, I put in a little bit, and I got back a lot. Okay? And again, you just write numbers like, imagine if you're, who's not here today, who's absent? Okay, she doesn't watch the video, and she just sees 30, 140. Am I supposed to know that? Is it subtract those? Where do you multiply those? Where do you get those numbers from? You're not going to understand it. That's why you really all have to know. And at the end of this period or at the beginning of the next, I'm going to show you again how to get to my website, all right, to be able to get onto the YouTube things. Because it makes a lot more sense now, okay? I say spontaneous or not. Spontaneous, like, for example, you might... an example of a spontaneous reaction would be burning this piece of paper. Okay, and I'll use this as an example, paper burning, because if I put, it's not bursting in the flames in my hands. All right, it's happening kind of slowly right now. If I were to look at this paper a couple hundred years from now, what will it look like? Yellow, brittle, probably pick it up and it fall apart in your hands. It's burning. Right now, it's combining with the oxygen in the air. It's just doing it really slowly because it's got this hill in the way. Can't get over that hill. Every now and then, a molecule gets enough energy to get over it just from the environment, but it doesn't happen very fast. But if I give him a push, if I give him a little push, hold on. I already had it on there. If I give him a little push over that hill, and how can I give him a push over that hill? Put a match to him, right? The whole thing burns. Because once he gets to the top of that hill, what happens? He's going to go the rest of the way by himself, right? And as each of these guys gives off energy, it'll be enough energy to make the guy next to him go over that hill. And that's a spontaneous reaction. It happens, that's the whole basis of our, society. We burn things. Okay? Not that we're all arsonists, but how'd you get here this morning? You drove in a car. You burned something, Your cell phones. You're not burning anything with them. Really? How'd you charge it? Something got burned. All right, unless it's nuclear power, all right, something got burned. Oil, coal, natural gas, something got burned, and that gives off energy. It's a spontaneous reaction, kind of a big deal for us. All right, good enough. Now, before I leave this guy, I just want to say, you could memorize your way through this. And I know there's a lot of you who like to do it. A lot of you, and I was one of them, I think some of you are like that. I know exactly where that was in my notes. I can picture it. Upper left-hand corner and this. I know you. You're all probably, a lot of you are in here like that because you're in the honors class. You probably are like that. But you know what? Eventually, you have to get to a point where you're not just memorizing everything. Can I just look at the graph and figure out what's going on? I can answer virtually every question about endo or exothermic by just either the name that exo or endo tells me, or the shape of the graph tells me every answer I could ask you. Because here are the questions I might ask you on the test. I might give you that graph and say, is this endo or exothermic? All right? I might give you that graph and say, is energy absorbed or released? I might say the reactants have more or less energy than the products. I might say, does it take more energy to break the reactants? Is it more likely to be spontaneous? Those are the same things I'm answering here. I will give you, I'm guaranteeing you this on the test, I will give you this graph. Giving you that graph, is that enough? Isn't that enough that you don't have to memorize this, but rather could just read it? Just look at the graph? Yeah. Because I know, if I asked, who has, reactants have more or less energy than the products? It's obvious. The reactants have more energy than the products, right? If I asked you, is energy absorbed or released? If it started here and it ends at a lower energy, what must have happened? Energy was given off. It was released. Same with the opposite one. Energy absorbed or released must be absorbed. It started low, ended high. So I can answer that question. I ask you, this is endo or exothermic. Once I know energy is released, exit, expel, the word tells me that it's exothermic, right? And once I know that, and I see the shape of the graph, you just look at the shape. Much more likely to be spontaneous than a graph that's going entirely uphill, right? Now, ball rolls downhill, not uphill. And finally, I could ask you, does it take more energy to break up the reactants, or do you get more energy out of the products? Again, you can answer that question just looking at the graph, realizing I put a little bit of energy in, I got a lot of energy back. Okay, that's an exothermic reaction. So it helps to understand chemistry rather than memorize it. Okay? All right, I'm going to actually, I kind of have to, because I have the video running, I'm talk about a few more things here, because I still have to give you those voting things. Well, let me finish this up first, before he gets back here to collect those. Activation energy. There's something called the activation energy in both of the graphs that I kind of kept out of there. I want to talk about what that is. I'm going to use an AE to abbreviate it on the graph. Okay? Activation energy. What is it? Well, it's that push. It's that match you need to get the guy going. It's that push you need to get him over that hill. The activation energy is the amount of energy it takes to get this guy up to the top of the hill, to the transition state, and then he'll go the rest of the way by himself. It's the energy required to break the bonds that initiates the reaction. Once you give it enough activation energy, the reaction will go the rest of the way by itself. You don't have to keep doing anything. And by the way, that applies to both endo or exo. That applies to both, people, because it's just that the activation energy in an endothermic one like that is pretty high. It's got a larger activation energy probably. Well, I mean, it all depends. Then certainly versus how much you get back than in an exothermic reaction. But that's what the activation energy is, the AE we're going to call it. And that will be this spot right here, AE. Okay? You can label that on the graph. I might ask you to label that on the graph. What's the activation energy? It's the amount of energy from here to there. That's what the activation energy is. Label that on that graph. And if we were to go back to the other graph, I'll label it on that one in a second too. AE, we'll call it, for activation energy. Y'all put it there? Okay. And if we go back to this graph, it would be what? Distance. Right there. It's already labeled for you there. Okay? AE. From the top to the start. Okay, that's the activation energy. Some people make a mistake here. All right. Some people make a mistake. This is the activation energy. On the test, I've seen this. That is the correct answer. People will say, oh, the activation energy is here. Because they think it's just a small part of the hill. No. It's the amount of all the energy it takes to get it to the top of that hill. Then it goes the rest of the way by itself. Okay? That's the activation energy. That's going to be important when we start talking about catalysts very soon. Well, actually, that's not true. We're going to do lab stuff second half of today and then lab the rest of this week. So not tomorrow, but next week we talk about that. All right? All right, what do we got? It's over 25. I have just enough time to cover one last thing. I told you a minute ago. Well, you know what? No, I'll save that for here. I want to pass these out in case he gets back, and we'll stop it right here.